consider a lap joint, and then type of riveting is a diamond riveting is there here. So we solve this problem. Then we'll take another problem. Now we'll take on butt joint. So earlier one it is lap joint. Now we consider another problem on butt joint. And also here this joint is also used for a structural application. So we want to see how we can solve this problem also. We'll discuss this one also. You first note down this problem, then we'll go through the solution also. So take 5 minutes for noting down. Once you complete it, just inform me so that we'll discuss the solution also. Two flat plates subjected to a tensile force capital P are connected together by means of a double strap butt joint as shown in figure. So you can clearly see here there are two cover plates. So therefore we'll call it as double strap. Of course the joining plates are kept side by side. That's why we'll call it as butt joint. The force P is 250 kilonewtons and width of the plate W. So this W value is given it as 200 mm. The rivets and plates are made of same steel. That means whatever may be the material for the plate as well as for the rivets, it is same and they are made of same steel. So therefore, whatever permissible stresses they are given, those are applicable for both rivets as well as plates. So that is the meaning of this. The rivets and plates are made of same steel and the permissible stresses in tension, compression and shear are 70, 100 and 60 Newton per mm square respectively. Then calculate 1. The diameter of the rivets, 2. The thickness of the plates, 3. The dimensions of the seam. That means you need to calculate what is the pitch, what is transverse pitch or back pitch, and you need to calculate what is the margin also. Then finally you need to compute what is the efficiency of the joint. This is the problem. So for that it clearly has given the joint also. The joint is also like this. Both the top view and front view and top view is given for your joint. So from this joint you can clearly imagine how your joint is going to be. Here it is a double row. So there are 2 rows of rivets for each plate. So we'll call it as double row, double strap, butt joint with equal thickness. The cover plate thickness width is equal here. Top and bottom are having same width only. It's not unequal. So he asked us calculate what is the diameter of the rivets, what is the thickness of the plates, and then what are the dimensions of the seam. Then what is the efficiency of the joint. Is it over? The noting down of this one problem?
Yes, sir.
Okay. You need to note down the figure also. Both you have to take. Even in the examination, sometimes they may ask draw the joint also. Not only design, they will ask design and draw also. They will ask like that. Design and draw the joint also. So you need to neatly draw this diagram. So that is important in the examination point of view. Okay, Rahul, coming to this particular problem, actually this is not a design problem. It is only an analysis problem. So he has given everything. He asked us calculate what are the values for maybe what is the diameter of the rivet, what is the thickness of the plate. Maybe part of it is design problem only. And also asked us calculate what is the efficiency of the joint also. See, like I already mentioned, maybe in the previous class, I have shown some pictures in which every picture I shown that this is the repeating group and this is the repeating group for this section. Like that, I showed so many pictures to you. So whenever it is possible to identify the repeating group in the joint, then we'll design or we'll calculate the strength of the joint based on the repeating group. But here in this problem as well as in the previous problem also, if I take it, I am unable to identify the repeating section. So I cannot take this one as a repeating section because here you have 2 rivets. So in here you have 3 rivets. Like that it is going on. So I cannot identify the repeating section. So for this case, so therefore whenever it is not possible to design or not possible to identify the repeating group, we need to design for all the rivets. If it is possible, then we will design the joint only based on the repeating group only. So now coming to this particular problem also here, even this problem also, it is not you cannot clearly identify the repeating section here also. It is not possible to identify the repeat section. Suppose if I take something like this here, these 2 are the repeating sections, then here it is repeating, but here there is no repetition. So here you have only 1 rivet. These 2 are repeating, but here it is not repeating. So therefore I cannot take this one as a repeating section. So therefore what we need to do is we need to design or we need to estimate the strength of the joint based on all the rivets, not on the repeating group or repeating section. So to do that here, so that means if we understand that principle, that means whenever there is a repeating group is there, we can design or we can estimate the strength of the joint based on that repeating group. If that is not available, then what we need to do is we need to consider all the rivets and then we need to design for total width of the plate. So here first question what you ask is, so here we have a double row, double strap, butt joint is given here. So and it is subjected to some tensile force. He has given the magnitude of the tensile force is 250 kilonewtons. So now because of this tensile force, so in order to withstand this 250 kilonewtons of tensile force, what should be the diameter of the rivets? First question he has given that. Then what should be the thickness of the plates? So thickness of the plates in the sense this thickness T, that is thickness of the joining plates. What is the minimum thickness for the plates required? Then dimensions of the seam means what is the pitch, this pitch value, and then what is the back pitch value? That means pitch between the two successive rows. So here we'll call it as a diagonal pitch, something like this. Diagonal pitch, what is the diagonal pitch value? And then what is the margin also? So here he has shown all those things. So PT value we need to compute what is PT, what is T you need to compute, what is this margin M you need to compute. So those things already shown here. P you have to compute, W is given to you. Then finally you need to identify the efficiency of the joint. Okay, right. So now first to calculate or to determine the diameter of the rivets, what we need to do is we need to consider what is the shearing strength of the rivets. So while estimating the shearing strength of the rivets, you need to first identify that whether the rivets are in single shear or double shear. First, that is the point. Then you need to find how many number of rivets are there. That also important. So we know shear strength of a rivet in case of a single shear is nothing but 5/4 d square into tau. So this is the shear strength of a rivet when it is in a single shear. Suppose if here in this case butt joint, in case of butt joint you have a double strap, two cover plates are there, therefore each rivet is subjected to double shear. It is shearing here as well as shearing here at this interface. So therefore you have a double shear. Okay, if you want to visualize that double shear how it look like, I'll take you back to one more animation I think I have with me. Just you can easily understand that. Yeah, this figure maybe these are the repeating groups what we see in the earlier class. Yeah, okay, you can see it here now. If I take this is another kind of butt joint, but this butt joint is having the bottom cover plate is having larger width than compared to the top one. So that means here for this rivet you have only one cover plate. This top cover plate is not covering this rivet. So here we have only one cover plate. So now if I pull this plate something like this, so then what happens is you can see the picture here. So I'm pulling something like this here. So this is the main cover plate. That means this is the main plate and this is the cover plate. You can see main plate is this and cover plate is there. So main plate is pulling something like this and the cover plate is pulling like this. Then the rivet is shearing here. So only at one location the rivet is shearing. So that is at the interface of this main plate and cover plate. Suppose if you have two cover plates are here for this rivet, then what happens? I will show you that picture also to you. I'll come to that. One minute. Not this. Okay, I'll take another problem then. Okay, here. Okay, here you can see that now. In this, you can easily see. You can see. Okay, even also it is like this only here also. Yeah, you can see it here now. In this picture, it is clear. See, if I take this rivet, see, because of pulling up like this side, and then the cover plate will try to move along this one. If you're pulling like this here, the cover plates are pulling something like this, then in that case what happens to this rivet is, this rivet is shearing at this location, means the one half is coming like this, another one half is coming like this. So here this bottom cover plate is pulling like this, so you are applying a force for this like this, then the resistance of this rivet is will act something like this in this direction. If you take this cover main plate, if the plate is pulling like something like this, and the resistance of the rivet will act in the opposite direction, something like this here. So because of that, here you have a shear. So only one single shear is there in case of this rivet. Whereas if the rivet is covered by two cover plates, so here this rivet is covered by only single cover plate, that's why it is in single shear. Here you can see that this rivet and these two rivets are covered by two cover plates here. So now you can see, if I draw the free body diagram here, the top plate is pulling like this and bottom plate is like this, and this plate is pulling something like this. So therefore at the interface here you have a double shear. So the rivet will be shearing into something like this. So here this is corresponding to the interface of the top cover plate and the main plate, and then this is the interface which corresponding to the bottom cover plate and the main plate. So like this, the rivet will be sheared here and here. Two locations it is going to shear. So then this kind of situation, what we'll call it as double shear. So that means whenever you have two cover plates, then it is the rivet is subjected to double shear. Whenever you have only single cover plate, see here in this case we are taking only single shear. In the earlier problem also we have solved this problem. In this we consider only single shear. So I not use the two here, two. So only we use the single shear and we multiply by the number of rivets for this to calculate the total shearing strength. So that's it. So but here in case of this butt joint, since you have two cover plates, you need to consider the strength of double shear, not single shear. So that means here all the rivets, these two rivets are subjected to double shear. So therefore I need to multiply this one by 2 first. So therefore the shearing area is going to be 2 into 5/4 d square into tau is the shearing stress. So this is for one rivet, the shearing strength of one rivet. How many rivets I have? I have total 5 rivets for each plate. So therefore I need to multiply this one by 5. So therefore this is going to be the shearing strength of all the rivets. So why I am considering all the rivets here? Because again the reason is here there is no definite groove which is repeating. So therefore I will design the joint for all the rivets. So therefore 5 into the shear strength of each rivet. So I get the total shearing strength. If I equate this one to the applied load, here the applied load is PS or P. Applied load is 250 kilonewtons. If I solve this equation, he has given the tau value to you. That is allowable shear stress. Here allowable stress in shear it is 60 Newton per mm square. So in this equation only unknown is D only. So then I can solve for the D. So that's what I did here in this. So that is the calculation I am going to do it here. So this is the given data in the problem. He has given P as 250 kilonewtons, W is given as 200 mm, sigma T, that is allowable tensile stress is 70 Newton per mm square, allowable shear stress is 60 Newton per mm square, and allowable compressive stress or pressing stress is 200 Newton per mm square. So now to identify the diameter, determining the diameter of the rivets, I need to equate the shearing strength of these 5 rivets to the applied load. So that's what I did. There are 5 rivets which are subjected to the double shear. Here all the 5 rivets are subjected to double shear. So therefore your shear load is equal to 2 into n into 5/4 d square tau, where n is the number of rivets. 2 we are using 2 here because they are in double shear. So now if I substitute that, the given load is 250 kilonewtons, I need to convert that one into newtons, then it is 250 into 10 cube, which is equal to 2 into number of rivets is 5 into 5/4 d square into 60. So now if I solve this equation, only left side is known, right side only unknown is D. So one equation, one unknown, you can easily solve that. So if I calculate this one, so from this I get D is equal to 23.03 mm. But I cannot take the diameter of the rivet is 23.03 mm. There is some standard values for the diameter of the rivet. So I have to choose only that standard value. So How I can know what is the standard value for the diameter of the rivet? So what you have to do is you have to use your data book again. So if you open your data book, in the data book there is a table which corresponding to this diameter of the rivet as well as diameter of the hole. So if you open your data book, in that the table 9.15 is there. If you have a data book, you can open it. You can open it, and it is table 9.15. So in my data book, it is the riveted joints. The chapter is 9, chapter 9. In that chapter 9, it is page number 9.18. Maybe for you, you have some other one. So now you tell me. So I am not going to give you the value. So somebody accept that LE5 and that Suman. I'll pick someone else. So then you have to tell what is the standard value for the diameter of the rivet. So now you open your data book, then we'll see that. So whether you are able to pick that value or able to. Now I can easily know whether you have a data book or not also. It is easily identified. So now go through this. So I will come out of this, and then what I'll do is I'll ask you somebody. So in the data book, you need to tell me what is the value of the diameter of the hole, standard diameter. So from the calculation we got 23.03. But what is the value you need to take? That for that you need to use the data book. So now somebody can tell me that except I already put a condition, except roll number LE5 and that Sumant. So any other, if anybody is told the answer, then okay, I will go forward. Otherwise, I'll pick somebody.
23, sir.
23 attached to the 23 is the correct answer. 23 is the same. Load carrying capacity and load 23 equation. 23 weight calculate load and P and 5 into 2 into 5 into 5 by 4 D in place of D square. 23 square into tau is 60. Calculate, we are going to get 250 kilonewtons. You tell me that value. First 23 anna kada. So 23 ante mee design principle inga em ardham kala. Era 28 నువ్వే చెప్పింది ఎట్లా వచ్చింది 23 సబ్స్టిట్యూట్ చేసి లోడ్ ఎంత క్యాలిక్యులేట్ చేయరా మనం 250 కిలోమీటర్స్ లోడ్ క్యారీ అవుతుందని వాడు ఇచ్చాడు నువ్వు డయామీటర్ 23 తీసుకుంటే నీకు 250 కిలోమీటర్స్ క్యారీ చేస్తుంది ఒకసారి క్యాలిక్యులేట్ చేయి ఇన్ ద సేమ్ ఈక్వేషన్ in place of D you put 23 D is equal to 23 and calculate what is the value you are going to get. You tell me that value. Hey, మాట్లాడ 28 ఉన్నావా
249 kilonewtons వచ్చింది సార్.
మరి 242 కిలోమీటర్స్ నువ్వు అప్లై చేసిన 250 అయితే మరి జాయింట్ సేఫా ఫెయిలా దాని కెపాసిటీ 249 కిలోమీటర్స్ ఉందిరా నువ్వు అప్లై చేస్తున్న 250 కిలోమీటర్స్ అప్పుడు జాయింట్ సేఫా ఫెయిలా ఇట్ ఇస్ గోయింగ్ టు ఫెయిల్
ఫెయిల్ సార్
మరి దెన్ హౌ ఇస్ ఇట్ ఇస్ 23 ఇంతకుముందు ఎన్ని క్యాలిక్యులేషన్లు చేయలేదురా వచ్చిన వాల్యూ కంటే ఎక్కువ వాల్యూ తీసుకోవాలి కానీ తక్కువ వాల్యూ తీసుకుంటే ఎట్లా సేఫ్ అవుతుంది కదా. If you take lesser value, definitely the load carrying capacity is less than 250 kilonewtons only. So now you tell me what is the value you have to pick from. అసలు డేటా బుక్ లో 23 వాల్యూ లేదు అక్కడ నువ్వు ఏదో నోటికి వచ్చింది 23 అని చెప్పావు నీ దగ్గర డేటా బుక్ ఉందో లేదో నాకు తెలియదు.
సార్ జలాలుద్దీన్ సార్
ఏ టేబుల్ చూసారు నువ్వు
9.18 పేజ్ నెంబర్ లో చూసాను సార్.
ఈ టేబుల్ ఎంత టేబుల్ నెంబరు టేబుల్కి టేబుల్ నెంబర్ ఉంటుంది కదా, టేబుల్ 9.4 టేబుల్ 9.5 అని ఇచ్చాడు కదా.
ఎస్ సార్.
ఎంత టేబుల్ నెంబర్ ఎంత?
9.5 సార్.
9.5లో 23 ఉందంటారు అసలు? ఉందా? ఏం చూసా నువ్వు ఆ టేబుల్లో ఉన్న 2 రోస్ ఏంటి చెప్పు నాకు.
నామినల్ డయామీటర్ ఆఫ్ ది లిమిట్, డయామీటర్ ఆఫ్ ది రిపీట్ హోల్ సార్.
మనం మాట్లాడుతున్న దేని గురించి? రివిట్ హోలా రివిట్ గురించా?
రిపీట్ హోల్ సార్.
రివిట్ హోలా? నీకు ఇచ్చిన ప్రాబ్లంలో క్వశ్చన్ ఏంట్రా? క్వశ్చన్లో ఫస్ట్ క్వశ్చన్ ఏంటి? ఏమడిగాడు?
చూసుకోలేదు సార్. డయామీటర్ ఆఫ్ ది రిపీట్ సార్.
చూసుకోలేదా? ఏం చేస్తున్నారు మరి? ఏం ఫాలో అవుతున్నట్టు నువ్వు క్లాసు? నువ్వు రాసినప్పుడు కూడా నిద్రపోతా రాసావా? ప్రాబ్లం రాసుకోరా అని చెప్పా. రాసుకునేటప్పుడు కూడా డయామీటర్ రివిట్ అని రాసింది కూడా గుర్తులేదా నీకు ఆ మాత్రం? Okay, so in that, what is the standard diameters? If you look at it in the table 9.5, nominal diameter of the rivet, you have to look into that column.
24, sir.
Top row. You have 22, you have 24. So, then what you have to take? Which value you have to take?
24, sir.
24, sir. 24. So, which should be whatever value you got it, you have to take the higher value, not the lower value. So, if you take lower value, it won't withstand the given load. That is a wrong concept. So, always you have to look for the higher dimension. Next higher dimension. Higher in the sense, you cannot say it is 42. So, 42 is also more than 23 base. It is useless. So, nearest to that value you need to take. Okay, so what I'll do is, you have to use 24, but diameter of the rivet, just I assume it as 25. I can take it as 25 also, but from the data book, you take exactly whatever is given, you take that as a 24 only. So D, you got 23.03 mm, then the diameter of the rivet is going to be 24, and the whole diameter is 25. That is the condition you need to take. Diameter of the rivet is 24 and diameter of rivet hole for that condition is 25. You remember that one. So here, maybe I not typed it properly. This is the diameter of the rivet hole, not the rivet. So diameter of the rivet is 24 mm. I have to write like that. And diameter of the rivet hole is 25 mm. So that is the answer for the first question or first bit of the problem. Then second bit, what you asked is thickness of the plates. So second one, you have to compute the thickness of the plates. This thickness of the plates is computed based on the tearing strength of the plate. So for that, here he has given the two sections. You can clearly see here he has given one section YY and another section is XX. So that means either the plate can tear off here or at the section YY or at the section XX. Tearing means the plate is splitted into two parts. Maybe at this location, across this row or across this row. There is a possibility of splitting of the plate. That is what we call it as a tearing. Tearing of the plate across this row of rivets or across this row of rivets. But if I compare these two again, so like in the same previous problem what we discussed, see, in order to have the plate tearing off at this location, first these two rivets should be shear off. Means if these two rivets are failed by either shearing or maybe crushing, then only at this location the plate will be tear off. So that means again, if I compare shearing to the crushing, generally crushing is won't happen because the crushing strength, if you see here, crushing strength is 100 Newton per mm square, whereas your shearing strength is only 60 Newton per mm square. So therefore, crushing cannot be happen. Only thing is shearing may happen. So that means in order to find the tearing strength at this location, so what you have to do is you have to consider what is the shearing strength of this rivet plus the tearing strength of the plate at this location. So if I compare that strength, only if I consider the section YY, then here I have to consider only the tearing strength of the rivets. So therefore, this is going to be the weakest location for the plate when compared to this. So therefore, I will find the thickness of the plate based on the tearing strength of the plate across these two rows, across the section YY. So to find that, we know what is the formula for the tearing strength. The tearing strength is nothing but the width of the plate minus, here you have two holes are there, you need to subtract 2D. Which W minus 2D into sigma T is going to be the tearing strength of the plate, and that should be equal to the your applied load. Your applied load is 250 kilonewtons. So from that, I'll get this W value. So that's what you ask. What is the width of the plate? That is the second question. Width of the plate or thickness of the plates you ask. Okay. So even thickness also you get that from that equation only. So this is the formula for the tearing strength of the plate across this. You can use this one also, but if you use this one, you will get the higher value, smaller value for the thickness. If you use this one, you will get the higher value. So if you have any doubt in that concept, then what you can do is you calculate at the both the locations, and then you will get two T values. Out of those two, you have to pick the highest value. So obviously for this section only, you get the highest value. So you need to pick that value. So this is the formula. Your PT is 250 kilonewtons. That is 250 into 10 cube. W is unknown to us. W is given. Sorry, it is given as 200 mm. Then D just now we calculated. So that is the diameter of the hole. Here you have to use diameter of the hole. That is important because we are talking about the plate. So we are not talking about the rivet. So in the plate you have a diameter. You need to consider diameter of the hole, so which is 25 mm you need to take. So thickness is unknown to us, and sigma T is given. Sigma T is given as 70 Newton per mm square. So therefore this is the equation for tearing strength of the plate. 250 into 10 cube is equal to W is given as 200, and 2 into D, where D is the diameter of the hole. So 2 into D is nothing but 50. Diameter of the hole is 25 mm. That's what we have picked from the data book. Then into T, and sigma T is given as 70. So now again in this entire equation, the only unknown is T. I can solve for the T. T comes out as, if I solve this equation, T is equal to 23.81 mm. Again, here for this there is no data in the data book. So just I rounded it up to the 25 mm. If you want, you can make it 24 also, no issue. I take it as 25 mm for the thickness of the plate. Again, or else if you want, you can refer our data book also. He has given some minimum conditions for thickness of the plate. So if you open table number 9.8 and page number 9.20, it's the table title is characteristics of strong structural joints. So in that he has given type of joint. First column is type of joint, then diameter of the rivet, pitch of the pitch in mm, back pitch, margin, number of rivets in single shear, number of rivets in double shear, and efficiency of the joint, something like that he has given. But he has not mentioned about anything about the thickness. So I can't use the table now. Number of rivets, diamond joint, lap joint, butt joint, okay, recommendation value, okay. So anyway, those things are not given. So maybe that's why I approximately, for preservations he has given, but for structural joints he has not given the table in the data book. Maybe in our latest also it may be there, but in this book he has not given. So then what we'll do is we'll round it up to the T is equal to 25 mm. So that is the answer for the second part of the question. Then third part is the dimensions of the seam. So that means you need to compute what is the pitch value P, what is this PT, transverse pitch, and similarly what is margin value. So those three things he asked us. So now again this PT value and this margin value will pick from the data book. So that is always margin is equal to, if you open the data book, in that he has given, if you open the tables corresponding to structural joint, so it is there, diamond butt joint in page number 9.8 it is there. If you open that diamond riveted joint like that, he has shown a picture here. In that he has given margin M is equal to 1.5D. So you have to take margin as 1.5D. So that's what I written straight away. Here D is also diameter of the hole only you need to take. So 1.5 into D is nothing but 37.5. So this straight away you need to pick from the data book. So that is you have page number 9.8. If you refer that page, in that he has given this formula M is equal to 1.5D. Or else if you want generally in most of the riveted joints the margin is going to be 1.5D only. If you remember that straight away you can write that also. Then this one PT, distance between the row of rivets. So that is also given in the data book. That is distance between the row of rivets PB or PT. It should be greater than or equal to 2D. That is your equation 9.32. This margin equation is 9.31. That is M is equal to 1.5D. And PB or PT, which is 2D, greater than or equal to 2D. So that means the minimum value you need to consider is 2D. So I consider that one as 2D, back pitch, which is nothing but 2D. So D is again 25, so I'll get it as 50 mm. Then I need, that means I calculate, I identified this value PT or PB value, and margin is also over. Then I have to find what is this P also. So that equation is also given. That is equation 9.30 in the data book. The same page number 9.8. Pitch of the rivets is given by P is equal to, this is the relation, W minus 2M divided by N minus 1, where this N dash, where this N dash is number of rivets in a row where it is maximum. So that means here we have two rows here or there. So this is one row and this is another row. Here you have to consider the number of rivets where it is maximum. So in this row there are 2 rivets, in this row there are 3 rivets. So I have to consider this row, not this row. So that means your N dash is here 3. So W is 200 is given. 2 into margin, just now we calculated 37.5 divided by 3 minus 1. If you compute that, you get that one as 62.5 mm. So that means I identify the what is the pitch, this pitch value also. So that means everything is over now. Next, finally, we'll go for computation of the efficiency of the joint. So to compute the efficiency of the joint, what you need to do is we need to calculate all the 3 strengths. Then out of those 3 strengths, you have to pick the minimum value. Then the efficiency is nothing but least of PS, PT and PC divided by strength of the solid plate. So these are the things I can show. The shearing strength of the rivet joint. Shearing strength of the joint is nothing but the shearing strength of the rivets. So now I calculated the D value, but I taken the D value as 24 mm. So diameter of the rivet is 24 mm. So now if I substitute that one into this equation, I'll get what is the shearing strength of all the rivets. I have 5 rivets. So whatever calculations I did, I'll use those calculations to find all these 3 strengths now. So if I substitute PS is equal to 2 into N is 5 by 4, D is 24 into tau. Tau he has already given that one as 60. Okay, maybe wrongly I substituted here 25. It is, you need to take 24 only here. It will come out as somewhat less than this 294 kilonewtons. Then similarly I can calculate.
271 వచ్చింది సార్ అక్కడ.
Okay,
271.4 kilonewtons sir.
271
Yes sir.
Yes sir.
Okay, so I'll modify it. 271.43
kilonewtons.
43 kilonewtons. Okay. Okay, so then similarly, I'll compute what is the tearing strength of the plate. That is nothing but the tearing strength of the joint. Again, the formula is same, W minus 2D into T into sigma T. So I'll substitute whatever the data value. Just now I calculated this T value. So I'll use the T value and I'll calculate what is PT. So W is 200 is given, 2 into 25 here. Here it is 25 only. T is, we computed it, we have taken the thickness of the plate as 25. and sigma t is given as 20. So now it comes out as 262.5 kilonewtons if I compute that. Similarly, I'll compute the pressing strength or bearing strength. So pressing strength of the joint is nothing but number of rivets multiplied by the projected area of the rivet into sigma c. So if I substitute this, here also maybe I need to substitute 124, 125. N is, okay, D is 24 only. Here you need to substitute D is equal to 24. Projected area. So here the projected area is 24 into 25 into 100. If you compute this, how much you are going to get this one? Maybe around, you will get somewhat less than this. So that is going to be the crushing.
300 kilonewtons.
Huh?
300 kilonewtons వచ్చింది సార్.
300. That is 300 kilonewtons. So I computed all the three strengths. So that is shearing strength, tearing strength, and crushing strength. Out of all these three, you need to pick the lowest value as the strength of the joint. So therefore, your strength of the joint is going to be 262.5 kilonewtons only. So you cannot take this 300 or this 271. Whatever may be the least value in these three, you have to take only that least value as the strength of the joint. Then strength of the solid plate. So that means if I take all the two plates are without joint as a single plate, so then the allowable tensile strength in the plate is 70 mm and the dimensions of the plate is 200 is the width and thickness is the 25. So 200 into 25 is going to be the area of the plate multiplied by the sigma t is 70. I'll get it as 250 kilonewtons. So then your efficiency of the joint is nothing but the strength of the joint divided by the strength of the solid plate. 262.5 divided by 350. That is going to be the efficiency of the joint. 262.5 divided by 350, which comes out as 0.75 or 75% is going to be the efficiency of the joint. So like this, I can solve the problem. So only thing is what you need to do is here from now onward, data book is mandatory. So it is must. If you don't have data book now, then you cannot solve the problems on the riveted joints. So not only that, so this is only structural problem anyway. So if you remember some problems, some formulas, then it is you may solve the problem. But from next one what we are considering is boiler joints. So in the boiler joints, if you don't know the data book, you cannot remember all those formulas also. Definitely you should have a data book and you need to use the data book only, then you need to design the joints. Okay, anyway, we'll move to that one. So before that, so is this problem is clear or any doubt in this problem? If you say yes, it is clear, then we'll move on to the next one. $28.
Sir.
Adhendra, Meera?
Clear, sir. Clear, sir. Clear, sir.
Okay, right. LE1? LE1?
Sir, yes, sir.
Okay, understood.
Yes, sir.
Right. So then, so with this, we'll close the structural joints. So in structural joints, we have seen two types of joints, how to design it. First problem we solved for a lap joint, and this problem is on butt joint. Maybe you may get a different kinds of problems. So based on the procedure is like this. They may frame, if you want, you can frame in any manner. The problem is sometimes they may ask to design the joint, or sometimes they may ask to calculate these things like that. They will say, or sometimes they will ask what is the strength of the joint also. So like that they can give in any manner, but this is the procedure. If it is a butt joint, how you have to solve the problem is this one. If it is a lap joint, the previous problem. Okay. So now we'll move on to the next topic, that is design of boiler joints. This we already discussed this one, this solution. So I am skipping this. Okay, right. So we'll move on to the next one is design of boiler joints. So in case of boilers, if you know how the boiler is manufactured or produced. So anybody having any idea how they will produce, how the boilers are going produced?
Sheet metal.
Huh?
Sheet metal.
Sheet metal. Okay, right. So with sheet metal, how the boiler is formed? They will take a sheet and they will fold something like this, and they make a joint and they will fold it in a circular cross section, something like this, and here they will make the joint. So this is one joint. So with the joint, what you can get is you will get a boiler of required diameter. But if I want to increase the length, so only with one sheet I'll get only this much length. If I want to further increase the length of the joint, then what I need to do is I have to take one more shell like this, and these two, and I need to join these two shells by another joint. So here, if you see here, to get the required diameter, the type of joint here, you can clearly see that what type of joint it is. That these two plates are overlap or side by side. Here, this side, these two edges of the plate, this edge and this edge, they are kept side by side. So here clearly you can see that this type of joint, what we call it as in joint is butt joint, lap joint.
Butt joint, sir.
It is butt joint. Since the edges are kept side by side, so therefore it is a butt joint. So that means what type of joint here? What is the name of this joint?
Longitudinal butt joint.
Why this is longitudinal? Because it is across the length of the joint is across the length of the shell. So we'll call this one as longitudinal joint. So this longitudinal joint is, I'll tell you the reason why you have to go for only butt joint, why not lap joint. I'll tell you in the next, maybe in the next 1 minute. Or else here itself we can see that. So in the previous class, I already told you there is a disadvantage for the lap joint when compared to the butt joint. What is the disadvantage? In case of lap joint, since the line of action of the forces are not passing through the same line, there is a bending moment. Like that I told in the previous class, right? If you have a lap joint, something like this. So here this is the force, and here I am applying the force to this. So here the line of action of these two forces is not coinciding. There is some eccentricity. Because of this, there is a bending stress. That means if we compare the strength of the lap joint to the butt joint, the strength of the butt joint is more when compared to the lap joint. So that's why I already told. So that means here the strength of the butt joint is more. But why I have to use here? Why I require more strength along the longitudinal axis? See, you might have studied thin cylinders in your MOS, right? Thin cylinders,
Yes, sir. Thin and thick cylinders.
Okay, thin cylinder. Okay, thick cylinders are shell. This comes under thin cylinder only. So in case of a thin cylinder subjected to internal pressure, it is subjected to two kinds of stresses. There are, one is called circumferential stress or whoop stress.
Yes, sir.
Another one is longitudinal stress. You have these two kinds of stresses will be there. Out of these two, which one is maximum? Your formula for whoop stress, sigma h is equal to PD by 2T.
2T. PD by 4T, sorry, we can know.
Longitudinal stress is sigma L is PD by 4T.
4T.
So which one is the highest value, sigma h or sigma L?
Sigma H, sir.
Because in the denominator here I have only 2, here I have a 4. Other things are same, PD by T is same, but sigma L is have 4 in the denominator, sigma H is 2 in the denominator. So therefore, your sigma H is greater than sigma L, or else you can say your sigma H is 2 times sigma L. Exactly, your hoop stress is twice the longitudinal stress. So now, if this joint is going to fail, because of which stress it is going to fail? Hoop stress or longitudinal stress? See, hoop stress means it will act across the diameter. So that means it will increase or decrease. Hoop stress will increase, either generally it is a tensile only, so it will increase the diameter of the cylinder. So hoop stress will tend to increase the diameter of the cylinder, whereas the longitudinal stress will tend to increase the length of the cylinder. So that means in the length direction sigma L is going to act. It will tend to increase the length. So that means what happens is how it is going to fail? It is going to fail at this interface because of at the section. So that means in the across the length it is going to fail because of sigma L. Whereas because of the hoop stress, the diameter is increasing means it is, so what is, where is the weakest section? So here is the weakest section. So across the diameter, this is the weakest section. So now if the diameter is increasing, that means what happens is here the opening will take place. So if it is okay up to certain amount, if plasticity will form, that means the diameter is increases. So if it exceeds that limit, then what happens is across this joint it is going to fail. So that means because of hoop stress, the longitudinal joint is going to fail. So that means that's why here I will design a butt joint. So because the strength requirement is more for the longitudinal this longitudinal joint when compared to the circumferential joint. So we'll use here butt joint. Here the strength requirement is less. So therefore I'll use this one lap joint in case of joining two cylinders. So that means if I want to get the more length for the cylinder for this boiler shell, I will take this two such kinds of cells, one and like this. Then I will overlap this one and other here along the circumference. I'll make a lap joint. So this is how the boilers are prepared. So in case of boiler, you have two joints. There are two types of riveted joints in case of cylindrical boiler shell. They are called longitudinal butt joint and circumferential lap joint. So across the circumference, it is going to be the lap joint. Why? Because it is lap joint means the strength requirement is less, or else the magnitude of longitudinal stress is half of the magnitude of your hoop stress. So you can go for lap joint here. Whereas this circumferential longitudinal joint, it should be a butt joint. So in case of butt joint, it has a more load carrying capacity when compared to the lap joint. So that's why here you have a butt joint and here you have a circumferential joint is going to be a lap joint. Okay, that's what I written here. So then the plate of the boiler shell is bent to form a ring. Okay, this is the procedure. Just now I explained. The same thing is written here also. The plate of the boiler shell is bent to form a ring, and the two edges of the plates are joined by longitudinal butt joint. This longitudinal joint is usually a double strap, triple riveted butt joint. So this is also standard in most of the boilers. So this is the joint they are going to use. Simply say, suppose in the examination or in maybe some questions, if they ask you design the longitudinal joint for the boiler, means what you have to do is you need to design for this double strap, triple riveted butt joint. You have to default, you have to, whenever if is given the problem, design a longitudinal joint for the boiler shell. Means you defaultly you have to take it as a double strap, triple riveted butt joint only. So that means you need to design this joint. Okay, right. The longitudinal joint makes the ring formed from the steel plate. Okay, the circumferential joint is used to get the required length. So longitudinal joint is used to make the ring. That means to get the required diameter, we need to use longitudinal joint. So to make the required length, we need to go for the circumferential joint. For this purpose, one ring is okay. That means if you want to make a circumferential joint, or if you want to increase the length of the boiler shell, one ring is kept overlapping over the adjacent ring, and the two rings are joined by a circumferential lap joint. So that means the circumferential joint is going to be lap joint, and the longitudinal joint is going to be the butt joint. That is the point you need to remember. So once you understood that, then what you do is we'll try to design what is this longitudinal butt joint. So I think I have some picture of it. Okay, anyway, I think it is somewhere else. Okay, we'll see that. So now to design this longitudinal butt joint for a boiler shell, first we need to compute what is the thickness of the plate we need to consider. So that means I want to manufacture, just now I shown the picture, that is here. So first I have to compute how much thickness I need to take for this plate. So then, that means if I want to create the shell, what is the thickness I need to consider? So how I can get that one? Again, that I will get from the formulas of that thin cylinder. So the thickness of the cylindrical shell, the thickness of the thin cylindrical shell subjected to internal pressure is given by, this is the formula. So earlier what I told is your sigma x is equal to PD by 2T. PD by 2T. But I want to calculate thickness, not sigma h. So then the sigma h will come here. So therefore you will get your T is equal to PD by 2 sigma T. Where here the sigma T is nothing but it's not hoop stress now because we are talking about the design. So the sigma T is going to be the allowable tensile stress in that plate, in the boiler shell or maybe that plate. So from that, how will compute the sigma T? I am taking some material for this plate, for the shell. So if I know the SUT of that shell, SUT by Fs is going to be your sigma T. SUT by Fs is going to be your sigma T. So now using this, I can calculate the thickness of the boiler shell. So that means while designing this joint, first thing you need to calculate is you need to calculate the thickness of the boiler shell. So now this formula is there in your data book. So now if you open your data book, again in that, yes, given the first one is design of the, again the chapter 9 you need to open. In that chapter, first table, that is design particulars and equations he has given in page number 9.3. So the boiler and axially loaded structural joints like that he has given. So in that, if you go through that page, so first formula, thickness of the boiler plate he has given in the first formula only he has given. But if you look at that, what he has given it is T is equal to PD by 2 sigma T into eta L, like that he has given. But what I have written here, it is somewhat different. Why it is different is, anyway, that is the actual value, we come to that also. Where this T is the thickness of the boiler shell, Pa is the internal pressure and dA is the internal diameter and sigma T is the allowable stress. That's what I written. Thickness of the cylinder, internal pressure, inner diameter of the cylinder, permeable tensile stress for the cylindrical material. The plate of the cylinder wall is drilled. So here in the data book, if you look at the data book, so you got, this is the equation you have. Here there is a efficiency of the term is also there. Why we are using efficiency here? Because just now we discussed the joint is made by the rivets here. So in order to make a riveting process, you need to drill the holes in the boiler plate. So this drilling of the holes will make the plate is weak. So that means it is a weaker one when compared to the solid plate. So therefore, to include that weakness in the plate because of drilling of holes, you need to include the efficiency of the joint also. So if I include the efficiency of the joint, then this is going to be the formula to compute the thickness of the plate. The plate of the cylinder wall is to be drilled for rivets. The weaker section passing through the rivets holes will not be as strong as solid plate. So therefore, the ratio of strength of the joint to the strength of the solid plate is expressed by efficiency of the joint and is denoted by eta. So therefore, modifying this above this equation, modifying the equation for T to account for this weakening effect, our equation for T is equal to Pi di by 2 sigma T into eta. So that's what he has given in the data book. That is the formula he has given in the data book. So and also he has given there are the efficiency values also. No need to compute that. So if it is a single riveted joint, your efficiency is going to be 0.6 to 0.8. If it is a double riveted, it is 0.75 to 0.85. If it is a triple riveted, it is 0.8 to 0.9. That means based on your requirement, so you can choose whether it is a single riveted or double riveted or triple riveted. So accordingly, you need to calculate the thickness. If it is a single riveted, here you need to take the efficiency is between 0.6 to 0.8. That means let us say I have chosen 0.7, accordingly we get the T value. Or else if I want to design for a double riveted joint, then I'll go for that. So, but like already told here, generally in case of this longitudinal joint, it is going to be double strap, triple riveted butt joint only. So that means it is a triple riveted joint means you need to pick the efficiency of the joint is in between 0.8 to 0.9. So you need to take that as 0.8 to 0.9 you have to substitute. So based on that, you will get the efficiency value. So then based on that, you need to compute the T value. So that means here we are calculating T in a single, not in a single step. We have to calculate T in 3 steps. Or else, okay, first this is the expression. If you take the efficiency of the joint is 100%. If you assume the efficiency of the joint is 100%, then this is the formula you have to use to compute the thickness of the boiler shell. If it is less than 100, then you have to include the efficiency also, then you will get it. So still it is not at over, then you have one more condition, that is further if what happens is during this fabrication process, the wall of the boiler shell is subjected to thinning due to corrosion. So that means if time passes, so the walls, that means that the end of the plate is subjected to corrosion, so which reduces the useful life of the shell. So provision has to be made by suitable increasing in the wall thickness to compensate for this thinning due to corrosion. So that means if you want to include the corrosion allowance also, then your equation for the thickness you need to modify further. So that is going to be, this is the final expression for thickness of the boiler shell. So this is the expression if I consider only the efficiency of the joint, if I ignore the corrosion resistance or corrosion allowance, not resistance, I have to use this one. Then if I include the corrosion allowance, so I need to include that also. Generally, the minimum corrosion allowance of 1.5 to 2 mm is used in calculation of this thickness. That means the value of CA, that is CA is nothing but corrosion allowance only. It may be approximately equal to 2 mm. So therefore, like this you can estimate the thickness of the boiler shell. So I think we'll continue already 3:20. So I'll stop at this point. Maybe at least from next class onwards, you be ready with the data book also for the class, because now onwards we will frequently refer the data book. Without data book, we cannot go forward here. So be ready with the data book for the class. Then we'll move on. Maybe we have a class on Wednesday, Monday you have examination, so we'll lose one class for that because of that examination. Even I think even on Tuesday also we are going to lose the class. On Wednesday we are going to get 2 classes are there. So on Wednesday we'll complete this design of this longitudinal butt joint. Maybe if time is there, we'll try to take circumferential joint also. But only thing here is you have to be ready with the data book. So because without data book you cannot go forward. So everything will be data book. See, whatever formulas I showed it here to you, those things are there in the data book also. Just I am explaining you why you are what formula you have to use for the what parameter. So that is the only thing I can do it here. Okay, right? I think now I'll stop at this point. If you have any doubt, then we can discuss. Otherwise, if you have another class, you can go and join that. And I think Saturday you don't have any additional class. I think so. You have a class?
Yes, sir. Can class?
Yes, sir.
Oh, okay. Then go and join the class. Maybe it's doubts class only. Then go and join the class.
Thank you, sir.